There's no penalty.
Penalties?
For not having a rough draft. It's just if you have some more written, you know, I'd like to see it. All right, other questions? No questions? No, it's good. No. Activities? You mean what? Activity being?
Delta H knots, delta S.
Do you have to memorize them?
Yeah, like appendix D, do you have to
No.
memorize it?
Are we going to have the
Equations? Mm-hmm. The main equations you'll have.
Like delta H naught equals to delta G naught equals to delta H naught minus T times delta H naught.
Yeah, that kind of thing. Those you'll have.
Yes.
Some of the equations you derive, like they put together two other equations. That you won't necessarily have on there. And so, yeah, major equations. Okay, other questions?
For number 3, it's asking which species has the lower entropy, and it's calcium or calcium ion or hydrogen ion.
I have a computer there. I'm going to bring it up. Thanks. Which will exam 19A?
Yes.
Number 3? Which species has a lower entropy? That should be easy.
Right, it should be A, right? Is that straightforward?
I thought it was going to be easy.
Oh, wait, did you ask that question? But, I don't know. It is a...
No,
Well,
wait.
he laughed when you said
I'm asking stuff.
I said this should be easy, and then the answer I got was A, which wasn't what I wanted
so
to hear.
C.
It should be easy.
C. C? Right, because one of them goes by Kelvin and another one goes by, no, but they're both cations.
No, you're right.
So it's C.
Actually, you're right. A's the correct answer. Sorry.
Wait, why am I right?
Why are you right? You tell me why you're right.
Okay.
Has a negative entropy.
Cool, yeah.
No, negative doesn't. You don't say it has a negative entropy because nothing has a really. The negative just means it's lower than 0. And so, would you say like it's a really cold day? The temperature is negative today.
No.
Well, it depends on what scale you're looking at, because on the Kelvin scale it wouldn't be negative, you know. And so, in this case here, this negative just means lower than 0. And H plus is it. So A is correct.
So you wanted to see if we can read?
Right, wouldn't that be way too simple of a question, guys?
No.
It's a very hard question. We need one of those on our test.
I mean, you fooled you.
It could be more complicated. You know, if I gave you like a Kelvin versus a Celsius, then it would be more complicated.
Okay, so we just have to know which scale it's going off of.
Yeah.
Right. Okay.
going with entropy rules, I guess, like, so I'm looking at number 4.
4 is C.
I know we know it's C, but is there actually a lowest one, or just because C is none of the other ones?
You know it's C. Why is it C?
Because I remember I looked in the book and I found one that happened to be lower than 500,
I was
so,
hit and miss.
right?
Question 4, right?
Yeah. Remember we found that one that was lower than 500, right?
Yeah, we saw one that was
So,
lower than
Are there
500.
like
So you take none
definite
of
like
these.
minimums?
Right, that's what I'm asking. Are there actual minimums or just because?
No, this is a trick question.
Yes.
Right, do you see it as a trick question? Why is it a trick question? Because what is the lowest temperature? Minus 10 or 0?
0.
Minus 10 or 0?
0 Kelvin.
Depending on what scale, yeah.
Depending on what scale. And so it's not necessarily none of these. So if you don't have the scale, right, then you got to say that the lowest temperature or the lowest entropy will be 0.
Because so when we have negative entropy, it's because
Well, let me ask you this. Let's go. On this chart, what is the lowest voltage? We have minus 2.87. Is that the absolute lowest?
No.
What would you guess the absolute lowest is? Minus 500?
Negative infinity.
Negative infinity? What would the lowest be? You see, this is why we have an arbitrary 0, because if we knew what the lowest would be, then we could just say, oh, that's going to be 0. That's going to be the lowest, right? Well, and so, you know, in this one, you would just say, well, one answer you could say, and the best answer, I think, would be A.
Why?
Why?
We don't have a scale to measure stuff.
You don't know what the arbitrary 0 is, but you know what an absolute 0 is, so.
Let's say absolute 0.
It doesn't say, but
What if we assume that?
but if you said none of these, would that be correct?
It could be.
Yeah.
No. If the scale's absolute, would you say none of these? If I said what is the coldest temperature, 0 or minus 500, although minus 500 is not possible. Let's go with minus 400. Let's say minus 400, 0 minus 400. You would say none of these?
Oh,
I would
that's
say
more
need
information.
info. Need more info.
Well, need more info is not a choice.
Could we make one? Yeah. Make your own.
No, on all of them, need more info, need more info.
Would you like us to like write a little paragraph?
Need more knowledge about this stuff. I mean, let me consult it.
Is the negative?
No,
Is in Celsius?
What would you say if somebody asked you what's the coldest temperature, 0 or, and they didn't give you the units, 0 minus 400, what would you say?
Minus 4, I would think.
No, minus 467 is coldest Celsius temperature, right? Or is that? No, a Fahrenheit temperature, minus 467. Is that right? It's been a while since I calculated. Minus 273 is the coldest Celsius temperature. 0 is the coldest. So at least you know the 3 coldest temperatures, minus 467, minus 273, and 0. Right? And so if somebody said, what's the coldest temperature, 0 or minus 10? What would your you could say 0 because at least that matches 1. And that would be the absolute scale. And so this one's the same kind of question. Minus 500? No, that's not. And so it's going to be 0.
if there were a not enough info answer, what would it be? Including it still had none of these, or I'm sorry, it still had 0, negative 500.
I'd still pick A. I'd still pick A because you know for sure 0 is the,
One of the lowest.
no, at the absolute lowest entropy you can have. What's most important in terms of your calculations? The Kelvin temperature or the Fahrenheit temperature? Which one do you use all the time? The Kelvin, because it has meaning to it, right? Do you ever put in the Celsius temperature in any of this chapter 19 equation? Never. You only use the absolute, and the absolute is what has meaning. Anybody can come up with a new temperature scale. You know, they'll call it degrees Z or something like that, you know, and define 0 in a different way. But nobody can come up with a new absolute scale. I mean, that's fixed. So if there's one thing that's fixed, it's the absolute 0 versus the arbitrary 0. And so I would still pick A. All right, other questions on this? I had so many questions this morning, I didn't get a chance to talk about anything else.
I guess also number 20 was typical and usually higher, yet unusually low.
Aluminum sulfate is at 290 Kelvin is a solid liquid gas. Solid. Solids typically have entropies from 0 to 1,000?
200.
0
Okay,
to
0 to 100.
0 to 100. It's unusually high.
But that's because it's a solid. If it was
Yeah.
something else, then it would be on a different
If it was a
scale.
gas, it would be typical.
Well, how do you know it's a solid? Is it just, you just know?
Solubility rules.
No, there doesn't have to be water around. Like, it could be sodium chloride. Aluminum sulfate is actually soluble. The reason I know it's a solid is because pure aluminum sulfate is salts are usually solids. So you gotta just assume it's gotta be pure. I mean, there's no AQ or anything else. And so that's how you know. Uh-huh.
So that question was kind of straightforward, but then the number 4 was really abstract, let's say. So there might be an answer, I don't know what is what.
What if somebody asked you, how deep can you dig a hole? You know? In other words, actually, maybe that's not the best one. Somebody asks you, how deep can you dig a hole? And then one answer is minus 3,000. Another answer is to the other side of the earth. What would you pick? To the other side of the earth, because at least, you know, that's as far as you can get, theoretically, right? And so, this is, at least one of those is correct theoretically, 0. And so, it would be the same kind of thing. I'd still pick 0, you know, because at least you know. And if somebody asks you, what is the coldest temperature, you know, or what is the coldest temperature possible? And somebody said 0 or minus 500. What would you pick? I'd pick probably 0, you know, because at least I know Kelvin. 0 is the coldest. Healthy eating compared to this. All right, what else?
Number 6.
Number 6. Which of the below can be determined with a fair degree of accuracy? This is Chem 1A question. A, B, and D are Chem 1A. But I didn't review it much this semester. In the past, maybe this semester I reviewed it a lot more, so I thought this was a fair question. But it's still a fair question because we talked about entropy. A,
Internal energy.
internal energy can be determined with a fair degree of accuracy? No. The thing about internal energy, where is the absolute 0 of energy? You know? B, enthalpy, no. It's because of the potential energy term, both in U and H. You know, where's the absolute zero? In other words, how far can you break things apart? You know? And so you break things apart into littler and littler pieces, right? The atom, into electrons, protons, and neutrons. But can you break apart the protons? Yeah. The even smaller particles. Can you break those apart? You know, how far can you break things apart until there's nothing left to break apart? When there's nothing left to break apart, that's your absolute zero potential energy. Right? And so that's why A and B. But C, you can determine, yes, there's a fair degree of accuracy. And D, you can determine high with accuracy too. You know, what we determine is delta H and delta U. Well, delta U is just equal to Q plus W. That, there's no problem with delta U. Delta U, as long as we use like Q plus W or something else, but we can't use U final minus U initial because we don't know what the absolute entropies are. And so the answer is just C and D. What else? Oh, you know what? I should have had this exam because I got asked this question and oh, here. Oh. Mm-hmm.
Is 7 false then?
Which one? 7. Entropies can be determined from theory or experiment. Is it false?
It's not saying change entropy.
Well, how are entropies determined? Tell me. How are entropies determined?
Experimentally.
Experimentally using heat capacity measurements, right?
Isn't that change entropy?
Mm.
It's absolute entropy.
Mm-hmm.
But is it always also determined from theory too?
Mm-hmm. When you look at the heat capacity versus temperature curve and you calculate the area, the total area under this is the absolute entropy, not delta S, but the absolute entropy. S can also be determined theoretically by this equation. Do you recognize this one? This is the equation I'd give you. S is equal to K ln W, which is...
So rate constant.
No. K is called the Boltzmann constant. S, this is called the Boltzmann equation. K is actually R divided by N sub A. We didn't actually do any calculations. In the homework, there's calculations you do. Calculate the number of ways, the number of possibilities that you have. And so, yeah, you could derive it both experimentally by measuring heat capacities or theoretically by determining all the ways in which to arrange things. One entropy that's very easy to determine theoretically is the entropy of a perfect crystal at 0 Kelvin. How many ways are there to arrange the particles of a perfect crystal at 0 Kelvin?
0.
One. If W equals 1, ln of 1 is 0, and so S is 0. We can't go any lower than that because we can't have like negative ways of arranging things. You know. Can we? No. Well, there's got to be at least one way of arranging things. Mm-hmm.
For number 8, would it be C and D, but then A also? Or it is A, right? Or did you say that there is no heat that's standard?
Just C and D.
That's all, right? Okay.
No A, no B. What else?
Number 17, it's B, right? CO2, because the more molecules there are, the higher.
More atoms.
More atoms.
You have the same number of molecules, it's per mole usually. And so the more atoms, the more ways of arranging those atoms. Not in terms of the bonds, CO2 is linear molecular geometry, but it's vibrating. And so more positions in three-dimensional space. For 17.
Can we see, like the limit to 16, like the question, or the question?
Number 12, the main types of entropy. I mean, I know there's positional and energy. Would that be it? D and B?
Yeah, B and D, and that's all.
D and B? D and B.
That's false, right? So you also need to take into account the surroundings.
Yeah, you have to look at the surroundings. So 16 is false.
Wait, it's false because what?
Because you have to take into account the system, the surroundings.
Right. Delta has a reaction of the system. And then the surroundings, we don't know what's happening with the surroundings. So just because the reaction or the system is increasing entropy, the surroundings might be decreasing it by an even larger number or factor, magnitude, making the whole thing negative.
Professor, number 13.
Yeah.
Number 13. I want to say it's like none of them. That's obvious.
Number 13.
Yeah.
Because the delta S is increasing because there's more disorder.
Yes.
I was about to guess that.
Delta S is increasing.
Okay.
And then, I guess for 15 and 18, they're both the same, but for 15, they're going from liquid to gas, meaning entropy is increasing, right, more disorder. And then for 18, would it be decreasing because it's going from solid to liquid to just solid? For 18?
Yeah.
So decreasing.
Decreasing.
Sorry, Professor, going back to 13. Is the delta S increasing because we're initially starting by not mixing them to mixing them?
It's increasing because all of a sudden they can be. Right now, if you think of mixing gases, when we do gas mixtures, we follow Avogadro's law style of gas mixture. That is, if we took 1 liter of A plus 1 liter of B, we're going to end up with how many liters of gas? 2 liters of gas. And so what we had was we had all the A gas organized over here. And then we put all the B gas organized over here. And so this is fairly well ordered because all the B gas is there, the A gas is here. But when we open the valve, what's going to happen? Well, all the A gas will diffuse over there, and the B gas will diffuse over here, and we end up with something like this. In which now, the B gas can occupy a lot more positions than before. So the number of ways of arranging the B gas particles in this container has just increased in fact, double if they're equal volume. The same thing with the A gas. And so the entropy has increased. Okay. Interestingly, the energy hasn't changed. So delta U is actually equal to 0. Because an ideal gas, the energy of an ideal gas only depends on its kinetic energy, not its potential energy. Because this is, let's say U A initial, U B initial. This is the absolute. So UA, you know, when we think about it, UA, the energy of this black gas consists of its kinetic energy plus its potential energy. But do ideal gases have bonds to break? What are ideal gases tetrahedral or octahedral molecules? No, ideal gases are just little points in space. And in an ideal gas, those points have no bonds. Those points have no volume either. They're just little particles. They have mass. Ideal gas will have mass. But there's no potential energy in an ideal gas, you know, because otherwise you'd have to have a different equation for each gas. For example, hydrogen has a different potential energy than oxygen, which has a different potential energy than nitrogen. And so to answer the earlier question, then we're going to come back to this. Which of the below can be determined with a fair degree of accuracy? So I have some nitrogen gas in this room. What is the energy in kilojoules per mole of the nitrogen gas sitting in this room? Just pure, or let me give you 1 liter pure nitrogen gas. Give me the kilojoules per mole of energy that has. This is the internal energy, is the total energy. Or I have this wash bottle filled with water. How many kilojoules per mole of energy is contained in the water in this wash bottle? Well, we can determine the kinetic energy because kinetic energy is just related to its temperature. But how much energy is stored in the bonds, in the atoms, you know, in the nuclei, in even smaller particles? You know, what is the total energy here? You know, have you ever heard that they're going to harness the energy of the atom, the nuclear chemistry, the atomic bomb, stuff like that? That means in, you know, just little tiny atoms of uranium or plutonium or even hydrogen. Look at the sun, you know. In these little atoms, there's a tremendous amount of energy stored. If you could harness all the energy in one water molecule, all of it, how much energy would that yield? Yeah, a lot of energy. In other words, you know, have you ever heard of E equals mc squared? You know, I'm sure everybody's heard of it. But if we convert the entire mass of a water molecule straight into energy, how much energy would that yield? You know, it would be a tremendous number. Huge. Well, anyway, we don't know this accurately, so there's no potential energy term. The only change is kinetic energy, and as long as the temperature stays the same, then delta U, you know, this is 298, this is 298, there's no change in energy. The same thing with delta H. There's no change in energy here. Delta H and delta U. I'm surprised nobody asked me about number 11.
Yeah, was that a
Wasn't it
typo?
C and D? Yeah.
That's a typo. No. C and D for sure will resolve. One was supposed to be the system, the other was supposed to be the surroundings or universe or something like that.
If one was system and one was surroundings, would it be one or the other, or also both?
Well, you know, I realized when people were asking me this question earlier, I realized that I wasn't specific enough in this question, in asking this question. You know, I should have said which of the below results in an increase in the entropy of the universe or something like that. But it's hard to say, you know, like A, B. For sure, C, D, and E. Would delta E less than 0 do it? What about delta H less than 0? That should do it because that should dump heat into the surrounding. But you know, that's for chemical reactions. For physical processes, sometimes it doesn't. You know, because yeah. We'll have to talk about it. Mm-hmm.
Number 14.
Number 14. The reaction, AB. What is delta H for that? Well, if you break bonds, does it cost you energy? Yeah. Or when I talk about potential energy, there's energy stored in the bond. That is, you know, when you break this bond, you have to use energy to break the bond. But when you form the bond, it releases energy. And so breaking bonds, endothermic, forming bonds, exothermic. So this is endothermic, delta H is greater than 0. So that should be non-spontaneous, right? Delta H greater than 0. And then, what? What's happening with the entropy?
It's going up.
It's going up. And so that's favorable. So one says no reaction, the other says reaction. We can change the significance of entropy by increasing the temperature. And so if the entropy is favorable, then this should be favorable at high temperature, so B.
Yes.
Okay, other?
For 19, is it delta S increases because it goes from less moles to more moles, even because they're both solid and gas, so it's not like it's state changing, but it's going from 4 moles to 5 moles, meaning more molecules, or how does that work?
If it were gas, going from 4 moles to 5 moles of gas, for sure. But what you're doing here is the moles of gas stay the same. You're going from 3 moles of gas to 3 moles of gas, so not much change in entropy.
Because it's more solid than it actually decreases?
Yeah, but the situation is you have a much more complicated solid, Fe2O3, going to a simpler solid, Fe. And so that's pretty close to just break even, because Fe2O3 should have a higher entropy, Fe should have a lower entropy. But there's 2 of them, so 2 times the lower entropy is going to be a higher entropy. I mean, you know. So it's pretty much break even.
So,
And so in this case, more info is required.
if there were an option that says remain the same,
Then you'd say, yeah.
Isn't the entropy of CO2 greater than the entropy of CO?
Yeah, but not much.
Not much.
Mhm.
So it's C.
Yeah, because the entropy of Fe is lower than Fe2O3. And so you don't know which one.
Could you give us another example like that? Just because we know that one, is there any other one you can give us and then we can determine that?
One like that?
Yeah, right on the board. Just because, like I said, I know the answer now because you just told me, but if it were on the test and I didn't know that specific equation, can you give us an example?
I did in class one. When we first started this, maybe. From the homework. Should we just look at that? Well, what do you know? Mhm. Maybe that's the one I did. Actually, I think that's the one I did in class. Huh. So let me think of a new one. We already did that one. What would you say about this one? Entropy increasing, decreasing, or staying about the same?
I would say increasing because it goes from solid and gas to gas and liquid.
Okay, but on the one hand, let's see.
Yeah, it's increased.
Right? Because it goes from something with low disorder and lots of disorder to something with lots of disorder and less disorder. No, sorry, more disorder than solid, right?
All right, so C6H12 being a solid,
Oh, no, that's,
Yeah, it can be entropy.
well, first we'd look at the gases. What would you say about the gases? 6O2 going to 6CO2?
Yeah.
Entropy should be increasing just a tiny bit. You know, it's about to break even.
How do you determine that between O2 and CO2? Like how close they are?
Well, CO2 because it's just 3 atoms, O2 because it's 2 atoms. That's all.
Okay.
And then, so we got 6 moles and 6 moles. So then we're looking at the entropy of the solid versus the liquid. Entropy of the liquid is higher. So yeah, I would say entropy is going up. We looked at some of these other ones here, like A. A should look familiar too. A is what? Going up, going down,
Decrease.
decrease. Yeah. B,
Increase.
that's easy, increase. C,
Increase.
increase. E,
More.
Also, when you use on the
E is a tough one because on one hand, you're going from 2 moles of gas to 1 mole of gas, so the entropy seems to be decreasing, but then you're going from silicon solid to gas. And so if I had to guess on this one, I'd say it's going up. But this one you might say, oh, I need more information.
I can check it out. So what was that? It was E, right? It says, in the solution manual at least, it said negative. It said 2 moles of gas.
Going to 1 mole of gas.
Yeah. 2 moles of gas. Plus solid.
But you'd take more info, right?
Hmm?
You'd take more info.
I could take more info because, okay, let's just guesstimate. Let's say silicon from 0 to 100. Gas from
100 to, oh wait.
100 to 200.
200 plus.
And so let's say silicon's 100, and then 2 moles of gas would be 200 times 2 would be 400, plus 100 is 500. And then on the right we have
Just 200.
just 200. And so, you know, my guess, I think, was off. The gas is more significant in this. Some others here. This one, A, what would you say? That one should be easy.
Yeah,
Decrease. Right. C is easy too.
increase.
Decrease. C, 24C.
And break even.
Break even. Close to break even or more information required. Yeah. D,
Increase.
well, that's good. All right, any other questions?
Number 10 of the other worksheet.
Experimental entropys are determined by
Heat, right?
Hmm?
Heat capacity.
Heat capacity.
Heat capacity.
B.
So just B.
Yeah. Work and heat, no. Gravity, no. Entropy meter would be nice, but no such luck. Pressure volume work, no.
I mean, we have a lot of work right now. No, we didn't do that.
I think in the workshop we might have had difficulty on number 5.
Did you go to the workshop?
Oh yeah, yeah. I think she may have been planning to ask you. I don't know if she got or not.
Number 5, which is used primarily to predict reaction driving force.
We just figured it was second law, but
What did I have on the? What did she say?
She said not to quote her.
yeah, exactly. She said she was gonna, she didn't want to give us a definitive answer because she didn't know 100%.
What would you guess?
I guess.
Yeah, we were gonna say second law.
Yeah, that's good. Second law.
Because we said the entry of the universe is always increasing.
Yeah, what's the first law?
The energy change.
Yeah.
And that would also go with number 2, right? The second law would be 2 would be D. Because as long as delta G is lower than 0, then it's spontaneous.
Yes, that's correct.
And just to get back to 11. 11 was C and D for sure, but was it A, B, and E at all? I know C and D were technically typos, but
Yeah, C, D, and E.
C, D, and E.
No, no, not E.
B,
E.
B.
B,
B, C, D.
but B when we're looking at like chemical processes. Yes. Even. Well, we'll just leave it. Okay.
Why is it that delta H increases entropy?
Well,
Or as long as delta H is lower than 0?
B, When we do this kind of thermodynamics, delta H, we try to keep the kinetic energy for, change the potential energy. We try to keep the kinetic energy from changing. And therefore, we do things a certain way. We start at 298 Kelvin, and we make sure we end at 298 Kelvin so that the kinetic energy stays the same. And they cancel out in our delta H. I shouldn't have crossed it out here. This is part of it. And so delta EK is 0. And therefore, this change is due to a change in potential energy. You could also have P delta B. And so when we're changing potential energy and it's exothermic, it dumps it to the surroundings as heat, or can. You can get work too, but if it dumps it out as heat, then we converted chemical potential energy to heat, which is increasing disorder, right? But this could be tricky because if we're looking at something like, and so this is why this question is not sufficiently clear, or it can be tricky because if we're looking at something like this, H2O gas goes to H2O liquid. Here, we're decreasing the energy, so delta U less than 0. Or did I say delta U greater than 0? As a choice? Is that? Yeah. Delta U greater than 0. Here I said delta H, right? And so here, if the delta U is greater than 0, what's happening to the entropy here? The entropy is increasing because we're going from a liquid to a gas.
But is it because of the internal energy?
Here, is the potential energy changing? No, because I start off with water, I end up with water. So there's no change in chemical identity. The only thing that's changing is the kinetic energy. If the kinetic energy is changing, then what this has to be is at T1 or T cold, and this must be at T hot. The kinetic energy is changing here. And so we're going from cold to hot. Well, H2O gas has a higher positional entropy than H2O liquid. And so the tricky thing was I didn't separate like this whole idea between positional and energy entropy. And so it made it a little bit confusing. Or a lot confusing. On our test, I'll try to make it a little clearer. Inferring.
Wrong class
Yeah, that was very polite. Most people would just, I think I'd do the same, just shut the door and run away quickly.
For the 19B, exam 19B, for number 10.
Oh, I prefer.
Or 11, 10, 11, they're kind of the same. They're literally the same.
They aren't.
They're not the same.
They're totally different.
What?
Well, it's standard versus non-standard.
Yeah.
Oh, boy. Can we go over both of them?
Huh?
Can we go over both of
It's
them?
identical.
10, circle all below that can potentially change delta G.
Yeah, temperature is one.
Temperature? Concentration, pressure, coupled reaction. Coupled reactions you can debate, but That's a way you can alter driving force stuff.
What does that mean by couple? Having multiple reactions going on at the same time?
But not just independent reactions, reactions that depend on one another. Did I do a coupled reaction example?
We do it.
Iron or something like that? Copper? Okay.
Oh, yeah. It's a copper oxide to copper and oxygen.
Yeah, so coupled reactions. Let's include that. 11. Which circle all below that can potentially change delta G naught?
Temperature.
Temperature.
That's all.
That's all.
Wait, what was 10? What were the answers?
All of them?
All?
10 is A, B, C, D.
That's correct.
12? Wait, what's? What about 12? Yeah. 12 or 12?
12.
Wait, 10 and 11 is the same.
No.
Oh, never mind.
Well, number 11, going back to that, is this. What can change this, let's say, what can change the posted speed limit? Me driving over the speed limit or under the speed limit? Will that change the speed limit? No. And so it doesn't matter what the concentration you put in there or the pressure you put in there. That's not going to change delta G naught because delta G naught is fixed for 1 and 1, right? 1 atmosphere, 1 mole.
So because delta G is not definitive and.
Right, delta G is like how fast are you driving. Delta G naught is what is the posted speed limit, right? And we make adjustments to the posted speed limit depending on how fast you're.
Like some fucking Toy Story aliens.
So 12.
12? You,
12 negative. I'm going with the small magnitude.
small magnitude, you think? It's large.
Very large.
Very large. Very, very large. It's very large because what are the cutoffs? You looked at the table in that chapter?
So like 200.
Like 300.
I'm not talking about max or min. I'm just talking about some kind of border line. I think I asked people to memorize between 50 and minus 50.
Yeah.
Oh, for spontaneity.
Yeah, between 50 and minus 50 it doesn't really favor one side or the other. But once we get above 50 or below minus 50, then we have a strong driving force one way or the other.
So that's 50 to minus 50 is like typical. Anything outside of that is either unusually high or unusually low.
Could we do number 17 on this? It's a true response question.
17.
Uh-huh.
Did we do that in class? No. All right, why don't you start? Did anybody do this?
No.
Nobody did this? Well, okay, why don't you start this and then I'll see what you've got. I'll give you a few minutes to work on it.